So this lecture is actually the continuation of the previous one. And in the previous lecture, we derived the equation related to the Raoult's law and the effect of the concentration of the solute on the lowering of the vapor pressure. So today I will give you some of the exercise to better understand what we have done in the previous lectures. And this is the first is in this exercise, I will give you the way how to calculate the vapor pressure lowering. And we will use the Raoult's law. And again, the detail is already given in the previous video. And here there are the two forms of the Raoult's law given over here. One is the vapor pressure of the solution is proportional to the mole fraction of the pure solvent. So more will be the mole fraction of the pure solvent, more will be the vapor pressure of the solvent in solution or vapor pressure of the solution. Or it is the lowering of the vapor pressure of the solution, more will be the concentration of the solute, more will be the lowering of the vapor pressure. So these two very simple relationships are important to calculate the vapor pressure lowering or the other calculation, which I will do in the next slide. So the data is given over here. Let's suppose you are taking 1 mole of the glucose in 15 mole of the water at 25 degrees centigrade, and the vapor pressure of the pure solvent at 25 degrees centigrade is 23.76 mm of Hg mercury. And now the first thing is to calculate the mole fraction of the water in solution. Because here I'm using, if you are using this formula, that means you need the mole fraction of the solvent. And if you are using this formula, here you would need the mole fraction of the solute. So if you put the mole fraction of the solute, you will get the directly the lower vapor pressure lowering, as this is our target. And if you put the mole fraction of the solvent, you would only get the vapor pressure of the solution. And then you have to use another very simple relationship to get the value of the vapor pressure lowering. So I am giving you the both way to calculate the vapor pressure lowering. One is this way. Actually, you have to first calculate if you are using this equation. So you have to calculate the mole fraction of the solvent. And the mole fraction of the solvent, this is given over here. This is the vapor pressure of the solution. I'm using this equation. And this is the vapor pressure of the pure solvent. This is the mole fraction of the solvent. So vapor pressure of the solvent is 23.76 as given over here. And mole fraction of the solvent you would calculate in this way. And in the previous video, I have solved in detail how to calculate the mole fraction. And this is a solvent, that means moles of the solvent divided by the total moles. And you are using 1 mole of the glucose and 15 moles of the water. And 15 mole of the solvent and divided by total moles, 1 mole of the solute and 15 mole of the solvent. And when you solve this one, you would get the answer 22.3 mm of Hg. So this is the vapor pressure of the solution. Again, solution means vapor pressure of the solvent in solution, because only the solvent will evaporate. So this is the lowering of the vapor pressure, because our target is how to get the vapor pressure lowering. And if you are using this equation, now you can calculate the vapor pressure lowering by this formula. This is the vapor pressure of the pure solvent minus vapor pressure of the solution, as we have done during the derivation of the Raoult's law. And this is the vapor pressure lowering, and vapor pressure of the pure solvent is again 23.76, and vapor pressure of the solution we have calculated by using this formula is 22.3 mm of mercury. And when you get the difference, your value is 1.5 mm of mercury. That means when you add 1 mole of the glucose in water, so there should be vapor pressure is reduced from 23.76 to 22.3. That means 1.5 mm of mercury, the vapor pressure of the solution is reduced. This is the one way. So I am giving you the other way to calculate by using the second formula as explained in the previous slide. So if you know the mole fraction of the solute, and you would put the value over here, you would directly get the value of the vapor pressure lowering. And again, this is the vapor pressure of the pure solvent. This is 23.76 mm of mercury. And if you want to get the mole fraction of the solute and know the moles of the solute divided by the total moles, and when you solve this one, you will get the same answer. It is 1.5 mm of mercury. Look at the value. This is also same. This is also the same value. So there are the two way, and actually this is not only the calculation, but by using this you will better understand what we have done during the derivation. So this is the now look at the effect of this solute. So in this exercise, actually this 1.5 mm of mercury vapor pressure is lower when you actually add the glucose, 1 mole of the glucose in 15 moles of the water. So let's see what would happen if you add 1 mole of the same 1 mole of the sodium chloride into 50 mole of the water. So I am just replacing the glucose with the sodium chloride, having the same number of moles. Then look at the way, or look at the value what is going to happen over here. And this is the, again, you have to first calculate the mole fraction of the water or the solvent. Okay, mole fraction of the solvent. And then here there is a little bit change to calculate the mole fraction of the solvent. Because this is again the same moles of the solvent divided by the total moles, or the moles of the water divided by the total moles. So mole of water are there 15, but here 15 are given over here. But if you add 1 mole of the sodium chloride, it will dissociate into 1 mole of the sodium and 1 mole of the chloride. So you have to separately put the number of moles for the cations and the anions. And this is the special case when you add the ionic or the salt into the water. Then you have to use the separately the same moles for the sodium and same moles for the chloride. And the total moles now, if you calculate a mole fraction of this water would be 0.882. Now, by using the same formula we have done before, let's why I'm using this one, or even you can use this formula. Here I'm just using one of the way. The second you can calculate at home by using this formula. Now I'm using the vapor pressure of the solution, and this would be the vapor pressure of the solvent, pure solvent, multiply the mole fraction of the solvent. The value of this one is this, and we have calculated this value. This is the vapor pressure of the solution is 21.0 mm of mercury. So what actually has changed during this one? It is the when you actually added the 1 mole of the glucose into 15 moles of the water. So what would be the vapor pressure of the solution is 22.3 mm of mercury. Okay. But when you added a sodium chloride into water, now the value is 21.0 mm of mercury. So if you want to get the value of the lowering of the vapor pressure by using the same formula, lowering of vapor pressure, this is the vapor pressure of the pure solvent minus vapor pressure of the solution. Pure solvent is 23.76 minus 21.0 as you have calculated over here. The lowering is vapor pressure 2.6 mm of mercury. So there is very important conclusion actually what is happening with 1 mole of the glucose into 15 moles of the water and 1 mole of the sodium chloride into the same 15 mole of the water. In case of the sodium chloride, lowering of vapor pressure is more as compared to the glucose when it is added to the 15 moles of the water. The lowering of vapor pressure is 1.5 mm of mercury. So this is the actually that mean sodium chloride is more ionic, or it is going to form a strong intermolecular forces or ion dipole forces with the water. So the water is having more difficulty to escape from the solution. So its vapor pressure is lower due to the more strong intermolecular forces. So it is having more lowering vapor pressure as compared to the glucose. So this is all about the calculation of the vapor pressure and understanding the effect of different solute into the same solvent, and it all depend on the forces of attraction between the solute and the solvent molecules. And these forces we have discussed in the one of the previous lecture. So here I am going to end this video and the lecture.